I'll keep with the short introductions. Marc Hesse is going to talk something about pore-scale controls on core formation in planetesimals.
Indeed. So, well, thank you very much. First, I'd like to thank the organizers for inviting me and all the presenters before me. I've really enjoyed all the talks so far, and I feel like I've learned a lot. So I hope you will also like my presentation. So, as advertised, we'll talk a little bit about core formation in planetesimals. Never mind. There will be pores that will be forming as well, so both. And this is really work that was done by my graduate student, Sohail Gambarzadeh, and he couldn't be here. But we had also some help from Jake Jordan, and he's not in the audience, but should be. Okay? All right, so, oops. Oh, well. So, first half of the talk will actually be about, sort of us exploring different features of texture equilibrated pore spaces. And the reason it's a classic subject, of course. The reason we're revisiting this is that I always felt that the effect of texture on this hadn't been explored. And I think we've seen some reasons yesterday in one of the field presentations about field observations that there could be some important effects of the pre-existing fabric on the melt distribution and on things like permeability and so on and so forth. So I just wanted to explore this, and so this is the result of this. Given that we have some people in the audience that come from mathematics and other related subjects that probably are not familiar with these concepts, I'll briefly introduce it, and then I'll introduce a level set method that we've developed that allows us to compute these on arbitrarily complex geometries, which is sort of what then allows us to look at the effect of rock fabric or texture. And then we'll just look at a bunch of interesting properties of these melt networks. And then in the last part, we'll try to think about what this means for things as the segregation of fluids that don't really want to connect. And the second application is really more of an attempt to try and test this theory, which has been around for a very long time, against some actual field observations. And it's bound for disappointment, of course. And so if you ask lots of questions, we just don't get there. And since I don't want to intrude on Rich's time, we'll leave it there. So I encourage you to ask questions. All right, so this is my one-slide summary. I'm sorry if I've forgotten some important contribution, but as far as I know, this started in the 40s with the metallurgists, and then the first geoscientists that picked up on this were the glaciologists. And this is probably still the best image you'll ever see of one of these texture equilibrated pores. And then in about the 80s, this community started picking up on these ideas. And then finally, in the 90s, it was realized that this may also apply to salt. And that's important because we're actually being funded by oil companies that are interested in fluid percolation in salt. And so I would define it as following, that essentially the idea here, textural equilibrium, means that the actual geometry of the pore space, so the liquid-solid interface, evolves to minimize the energy, its own energy, while maintaining a constant dihedral angle, which really just means mechanical equilibrium at junctions where two solid grains and the liquid come together. So one of these junctions, for example, would be here, right? So that's, and the other caveat is that all of this, of course, only applies under hydrostatic stress conditions, and of course we've seen multiple lines of evidence that shear stresses and other things may become very important. So what I'm going to say is won't apply to these situations, but I hope we'll still learn something interesting. So as I said, we're funded by an oil company. So the basic idea is if you have two salt grains, and we're on the pore scale, right? It's not a planetesimal, we're on the pore scale. So here's a salt grain, here's another salt grain or an olivine grain. Here's a brine or a melt, and here at this triple point they come together. And mechanical equilibrium simply requires that the ratio of the surface energies is proportional to this angle theta, which is the angle that's in the fluid here. And the other part that goes into the theory is sort of this idea that there's an energetic contribution. If a curvature contributes, that gives free energy of the material. And so in general, if you have high curvature areas, they will smooth out and evolve to some sort of constant mean curvature interface. And of course, this assumes that all the energies, surface energies, are isotropic, which is not true, as Paul has pointed out already. But everything that I will present will assume this. However, I do believe that the method that we've working with could be extended, okay? And so this could be looked at in the future. But for now, we're looking at isotropic systems. And then you're trying to put all of this together. And so what you're trying to do, and to make this, fully formulated problem, you need to add three things. You need to add the pre-existing geometry of the grains, which in our case will end up being quite complicated. So that in this case here, of course, it's just these lines. Then you specify the porosity. So this is not a dynamic problem. We're solving for a steady state, and we give the porosity. It's not the answer. It's something we feed in. And then you want to specify the dihedral angle, right? So you're solving for this constant mean curvature surface under the constraint of the previous geometry, under the constraint of the dihedral angle at the triple junctions, and under the constraint of the porosity. Dan is smiling and...
I'll tell you why. Private.
Okay. And I appreciate that. Yes, Joe.
And I presume, just because I haven't asked this question yet, that you ignored pre-melting at the junction.
That is a very good question. I'm told it's supposed to be the answer. No, we have completely ignored pre-melting here. And I would say that's, well, this could be another PhD project, most likely.
Just 1 second. R is radius of curvature.
Yeah, so this, okay, so here, this, just because the student at some point actually solved this problem. And so this is essentially a 1D problem, and in this case, it's just a radius from here outward. And it just goes to remind you that what you're actually solving is a nonlinear elliptic equation. And because it's nonlinear strictly, there could be multiple solutions. And there's a...
R is what again?
I should not use... So in this particular simple case, R is just the distance of the interface to the center of this, right? But since we're going in 3D, this will not. Sorry? So then you could write down a simple ODE that allows you to solve for this. And I just write it down because it reminds you that you're actually solving a steady nonlinear elliptic PDE. And the curvature itself actually is not known a priori. I tend to think of it like an eigenvalue, but I'm not sure if that's mathematically a legitimate...
Why isn't the... Stay with that for a second.
Yeah.
Why I haven't understood why the radius of curvature isn't constant on all.
It is constant.
It is.
And so the big...
In
so
2D.
Yeah. So the big difference between between 2D, well, between a one-dimensional interface in a 2D space and a three-dimensional interface in a a surface in a three-dimensional space is, of course, that you have much more opportunities for maintaining constant mean curvature, and that's what makes it interesting, and that's what leads to sometimes surprising results, right? Okay, so
that was why I was smiling, because Cheadle was my graduate student, and I set him off to do this.
And how did he fare?
He did a good job, and he never published it.
Well, he did eventually, right? So,
not really.
So there obviously are many more people have worked on this. I'm just, I'm sorry if I've forgotten somebody, but these were sort of maybe the first attempts to do this. And different people had different ways of solving this, but fundamentally everybody tried to solve for this interface, to have an explicit representation of this interface and solve for it, right? And fundamentally, somewhere under, even if it was some iterative process or something, fundamentally you're solving this nonlinear elliptic PDE. And to be able to do this, you need to have a single valued answer, right? And if you're in a complex Pore network, the answer is by definition not single valued. So they had to use these brilliant sort of symmetry arguments to cut it down, and you can see this very nicely here, to some small element where the interface is single valued, and then you assemble it. But of course, you can't use this to look at sort of complex shapes. And so we decided to kind of use a completely different approach. We use a level set method, which is, instead of an explicit representation of the interface, it's an implicit representation of the interface. And it's always useful if you have sort of complex geometries and topological changes. So this is one of our results that's sort of very similar to what you've seen on the last slide. And I don't really want to dwell too much on the numerical method, but fundamentally what we're doing, so the solid-liquid interface is represented by the levels, but one of the level sets of this function phi. And what we want is we know that it needs to be constant curvature, okay? And there's several PDEs that evolve a level set to constant curvature. One would be, for example, a curvature-driven flow. And it's also known that surface diffusion, which is this operator here, will also evolve your level set to constant curvature. Now we only care about the steady state. We don't care about transient evolution or the physical mechanism, although that might be interesting at later stages. So really we're just using this as a device to solve for the steady state in a really what is an iterative way.
So phi is your level set?
Yeah, phi is, well, so fundamentally this is a really hard equation to solve, at least for me. The good thing is that this is a standard problem with level sets. This is what level sets are really good at. So essentially your standard level set toolbox comes with this implemented. Okay? So this is a fourth order operator. You need high order discretizations, all of this stuff. And that was all there. So what we needed to add is, so first you need to remember what the grain geometry is. And so the way we do this is every grain is 2 level sets. One level set that remembers the original shape, doesn't evolve. And another one that is the solid liquid interface of that grain. And that of course we're solving for. So we don't just have one of these, but we have one of these for each grain that's evolving. Right? And they're all communicating, of course, because they have to maintain the dihedral angle, and there needs to be an overall porosity. And so the hard part is how you add these constraints into the system, and I give you the clean version of it. The simple answer is that this adds artificial velocities, right? So if you start off, we tend to start off with both level sets for the grain being the same, so there's 0 melting. And then, of course, the porosity is not what it's supposed to be. And then you add a artificial velocity to it that moves the interface outward and increases the porosity. And then as you approach the right porosity, this velocity disappears. And the same thing happens with the dihedral angle. Okay? And how exactly you formulate those, it's tricky, but it can be done. Right? And if you're interested in the details, there's a paper that has all of this written down. So the beauty of this is now that we're not limited to these simple truncated octahedra that people have looked at before, but we can look at sort of interesting, textually complicated cases.
The dimensions of VE is a vector, yes?
So in level set terminologies, different kinds of velocities that have to be treated different ways. But this is a velocity that arises because the dihedral angle constraint is not satisfied. And this is a velocity. This is a classic advective. The A just means advection. This is a classic advection term, right? The velocity times the gradient of the thing you're evolving. And this is a normal velocity, okay? And they have to be treated differently numerically. And but they're fictitious, so we're only interested in the steady state, right? So at steady state, those go away, and they just help us to, inflate the pore space if we don't have enough porosity, or shrink it. Okay, so now we can use this tool to look at various properties of these texture equilibrated systems, and the first one that I want to look at is sort of nucleation at textural equilibrium. And so I believe this is something that hasn't been really thought about. So I think everybody in this room has at some point seen this graph, this is the simplest version of classical nucleation theory, which says if you want to nucleate a new phase in a homogeneous medium, you're going to nucleate it because the volumetric Gibbs free energy of this phase is lower, and so this would reduce the volumetric term, which goes as r cubed, reduces the overall free energy, but you're creating a new interface, and that of course goes as r squared, and that adds energy. And if the nucleus is small, then you have a high area to volume ratio, and so initially this dominates, and it increases, reaches a maximum, and so then this is considered the critical radius, and after this, any further growth of the nucleus leads to reduction in the overall Gibbs free energy. And so that's something that you probably have seen in some kinetics or material science class or physics class. And then there's a wrinkle on this, that of course if you, instead of nucleating in a homogeneous phase, if you nucleate on a pre-existing interface, you are helping yourself because you've eliminated that interface which had a cost. And so here you see for the first time sort of the important effect of the dihedral angle. The lower the dihedral angle is for constant volume, the more you're going to spread it out, the more of that previous interface you're going to eliminate. And what's plotted here is simply the value of this maximum as a function of the dihedral angle. So here you have a sphere, and somewhere this, I don't know, it's probably 60. Somewhere here you've reduced it quite a bit, and if you of course become perfectly spreading, there's no penalty. All right, so So just out of curiosity, we wanted to see what this looks like for a nucleation at textural equilibrium. And so things are not radial anymore, so instead we're plotting as a function of porosity. That's why the bulk free energy term is linear. The Gibbs free energy is scaled with the surface energies because we have no idea what the surface energies really are, and it's really just conceptual more than anything. And from the computations, of course, we know what the interfaces are that we've created, we know what the interfaces are that we've destroyed, and we can do the sum, and you see the total sort of interfacial energy contribution is positive, very similar to the classic case. Then if you add those two together, you first get a maximum, and then it decreases, and so maybe there would be a critical porosity here, just like the classical case.
Nucleating the triple junctions.
Yes. So,
It's for
so
theta,
this is, so this is,
and theta equals 90.
yes, okay, so, sorry, yes. This will become important. So this is at relatively large dihedral angles, right? So the melt doesn't really want to wet the grain boundaries. But it's fundamentally the classical picture, right? It's a little complicated because there's a change in topology, but fundamentally it's the same thing that you see in the classic theory. And so then we repeated the same calculation for theta of 30. So now the melt wants to kind of spread out onto the grain boundaries. And so to our surprise, we found that so the bulk free energy, of course, is negative, that the interfacial free energy contribution is also negative. And so it's probably we haven't thought about this in depth, and it's not published, right? But it just goes, the main reason I want to show it is that there's actually maybe still some interesting things that we can learn about these systems. I think there's two things that are happening. Of course, the difference between the interfacial energies changes between here and here, and you're starting, the area of the liquid-solid interface starts getting closer and closer to the solid-solid interface that you're eliminating. So those areas start becoming more similar, and of course the liquid-solid interface starts becoming energetically more favorable as the dihedral angle dips below 60.
And what are you conserving when you do this? Are you
Well, there's
taking into account the difference in density between the solid and the liquid?
absolutely not.
That's
Okay, so
not work,
yeah. So let's phrase it this way. Certainly in this case, is where the melt is not connected, you clearly would have to take strains and that come due to volume changes and so on. I think in this case, so I discussed this with various people. If you imagined yourself, you had the crystals in sort of a bath surrounding it. The melt that's produced, if it's larger volume, could sort of just drain out to the side into a constant pressure reservoir. Then that's sort of what we'd be approximating here. But it's just an interesting, it's an observation that surprised us. Okay, and I just want to leave it there. And this is sort of as a maybe there's still some things that we haven't found out about these.
Is there an angle at which the interface free energy is 0 at the?
Yes. Yeah. So that's actually the way the student found this is. So we'll see later on that there's multiple solutions, and he wanted to know which of the solution actually has the lowest energy and is hence the proper minimum. And as he was doing, and for this he needed to calculate all the interfacial, all this stuff, right? And the transition is actually, I think, the interfacial energy is, or the 0 point is for these 3D calculations at 70 rather than at 60. And the 70 is when these guys would be essentially little pyramids with almost flat faces. And maybe that has something to do with it. So this needs more thought, but I think there's clearly interesting things happening here. And so it means fundamentally, if this is all carries through, that it's energetically very favorable to nucleate into sort of a textural equilibrium configuration, which may be why in nature there. Yes?
I've really missed this, but you're essentially calculating nucleation on 4-grain junctions. That's where the nucleation starts. That's why 70 degrees matters. On 3-grain junctions.
Yeah, so right, so along these edges, 3 grains come together, right? And then the corners, 4 grains come together.
But your nucleation starting at the 4-grain junctions.
So, nucleation, of course, nucleation implies that there's a progressing process, right? What we're doing is we're just calculating different minimum energy shapes for different porosities, right? So it's if anything, it's a succession of steady states. And yes, there will always be melt. So in all of our calculations, if the dihedral angle is high, the melt will of course form in these 4-grain corners. But if it's slow, of course, immediately it will also be along the grain edges. that helps. All right, so this was really just to pique your interest in what's going on. So this is a more classical subject here. So percolation threshold. So these systems are known to have interesting behavior in terms of percolation. So here are two constraints: the porosity increasing along the bottom, the dihedral angle increasing along the side, and all of these are computations of many, many grains, and we've just isolated one to be able to illustrate it better. And so the classic observation is that if you have, and then the same thing is here just with an actual plot, and these dots give all the calculations that we've done. And so one of the really fascinating things about these systems is that if the dihedral angle is low, you percolate at almost any porosity. And of course, this is the lowest porosity we can actually resolve in our computer, so somewhere down here. And then as you get, the dihedral angle gets larger. Here, these little pyramids that you get when it's 70, you need to grow the porosity to some point until these pyramids touch.
And that's a percentage?
This, yes, sorry, yes. let me check. Let me check with the student. Sorry, yeah, in percent, yes. Thanks for pointing that out. Anyway, and so then you can map out this percolation threshold, and it looks very similar to the ones that people have previously found. And this is one way of sort of kind of comparing what we're doing also.
How do you define percolation?
Percolation in this case is, so between, this simulation, the little pockets didn't touch, and now here it's percolating. Okay, and so it's maybe here.
Why can't you compute an arbitrarily small porosity?
The grid resolution. So this is all of this lives on a Cartesian grid, and so personally I think this is probably pushing it. Okay, there's some visualization. So there's multiple things going on. So there's one grid for the actual computation. For the visualization already, it really helps if you actually have a finer grid and interpolate your level set onto a finer. So, but anyways, it's just plain old numerical resolution. And it's a really expensive, awkward method, right? It's a fourth order thing. We're solving it explicitly. It's tiny, tiny, tiny time steps. So I'm sure it could be improved if the right numerical mind would put it. Anyway.
To talk about it, I don't want to press you now, but are you going to talk about permeability as well?
Yes. Yeah. So fundamentally, everything I've shown you so far is sort of a solid that's made up out of truncated octahedra, right? Like a Kelvin solid. And so not the hardest, so Hill would disagree, but one hard part of this research was to actually find an actual scan of a fully solid polycrystalline material where you have all the grain boundaries. So one of the things, we developed the method, and for a long time we couldn't find anything to use it on because it's really hard to do this. So we found one such data set, and it comes from Ludwig al. in 2009, and you need a technique called X-ray diffraction contrast tomography. And they don't just give you the grains, they also give you the lattice orientation in the grains. So it's really cool. We have a CT scanner in the basement. I asked our guys, can we do this? And, I didn't hear back from him. And so a week later, I was like, so? And he said, yeah, if we turn a football stadium into a synchrotron, then we could do this. And since we're at the University of Texas, this is not an option for us. But if this is an option for your institution, I'm happy to write a letter of support. Anyway, so this is of course not a peridotite or anything like this. This is these are metallurgists, physicists working on metallurgy. So this is some metal, but it has beautifully grains of different sizes and shapes, and so all the computations that you see from now on are on this particular piece of the universe. Okay, so we can just redo the same computation, and it gets harder to visualize it because of course it becomes a mess. But you see a similar thing. So here at 10 degrees dihedral angle, the difference now is the porosities are much bigger. They're given in percent. But at 10 degrees wetting angle, we're always connected. We can push this down to half. And the main point here is that the percolation threshold is pushed out to much, much larger porosities in an irregular medium than it is in a regular medium. And the reason, if you think about it afterwards, is sort of pretty obvious, because in the regular medium, all the pockets are separated by exactly the same distance, and they all touch at exactly the same time, and everything connects. In an irregular medium, all the grain edges have all different lengths, and of course the two pockets that are closest together touch first, and then it percolates, so to speak, up successively larger grain edges get connected. The other thing that we've noticed is when two pockets connect, they actually contract a little bit, which makes it then harder to connect over to the next set of pockets. And so together, all of these effects make for a very large, up to essentially almost 20% percolation threshold. And so, of course,
Percolation threshold is harder to define in this case because you have both isolated and connected pockets.
yeah,
So is it just the first time you can draw one line continuously from one side of the box to the other?
we discussed this at length, including the use of the grass fire algorithm. Now, so for us, percolation means that all three. So in our sample, and of course it depends on sample size, right? That you can go, you can traverse the medium from all three opposing faces. And so, strictly there might be sort of a little gray area where you can maybe go one way but not the other way.
Sorry if you've already said this, but when you change the porosity, do you convert some of the mass of the solid to melt, and therefore the total volume of your system is constant, or do the grains actually need to move apart?
No, the grains don't move at all. So it's a, yeah. So there's, if you come from conservation laws, this is awkward.
Do the pores then overlap with the grains? In the original configuration?
Yeah,
grains?
exactly. So
Okay.
yeah. So
All right. That's clear then.
yeah. So, and this is what all the previous calculations have done, right? So you have a grain, and then you just shave off the edges and call it melt. So in a simple way.
Do you eliminate small grains?
They eliminate themselves, yeah. I think, yeah. Okay, so anyway, so of course if you're in a sort of a mantle system, you'll never exceed, porosities down here, and in the absence of shear, of course, this is a pretty effective barrier to percolation, right? Okay, so one of the reasons that I was really, so all of this was just sort of kind of redoing previous work. One of the things that I was really interested in is, well, what is, if you have some interesting texture in your rock. And this is work that we did early on, so it doesn't actually use an interestingly textured rock, but a minimally textured rock. So this was before we found the irregular grains. The simple idea was, well, what happens if we just stretch these grains, right? So here's the isotropic case, and here's what happens if you stretch these grains. Okay, and so what can happen in these very simple stretched media, you can get the melt redistributing onto the faces that are parallel to the direction of stretching. And this is for dihedral angles that are low. Essentially, if the dihedral angle is below 60, there's a tendency for the melt to distribute itself onto the faces that are parallel to the direction of stretching. And when exactly this happens depends on the dihedral angle. And I think in an irregular medium, of course, there won't just be one transition, but one after the other, the faces will get wetted that are roughly parallel. So if you now increase the dihedral angle to above 60, then you see that the opposite, the faces that are perpendicular to the direction of stretching, get wetted. And you can see that it's going to be, so here they're just connecting, and here they've accumulated, and you can see that this is, it's going to be very hard to connect these, right? So you will need very large porosities if you wanted to actually percolate in this particular system. And so this did come, so it's just an example of, in 3D, so then you're like, is this really constant curvature? And one of the beautiful things with the level set method is you can plot the curvature, and I'll show you some plots of curvature on natural materials. And yes, largely it's all the same curvature, and then there's some crizzle, and you're not sure whether that's interpolation error, but fundamentally these are constant curvature surfaces.
Do you have any physical insight as to why he chooses these? I mean, he doesn't know.
Well, no, I mean,
stretch it.
actually, so why? Okay, so here I stretch it by 50%, right? But you could stretch it by epsilon, and that's what happened. And it's simply, so there's maybe two parts. So as soon as this edge is epsilon longer than this edge, and in some sense, so this regular medium that's just stretched by epsilon is sort of the worst case, I think. These two pockets will connect, and it's going to be much harder to connect in this direction. And then once these are connected, of course, as you increase the porosity, the circle here shrinks, and at some point
It's just that it finds the short edges.
it finds the short edges.
Okay.
Yeah.
But the problem because of the interconnection. Right? I mean, you're not looking at how one can change into the other when you stretch.
Yeah. So when all of these are
the things are isolated. So when you increase the porosity from 1% to 4%, it's not obvious that the melting will occur on those boundaries rather than uniformly, and if it occurs uniformly, then...
But then the argument would be that it would redistribute itself such that it minimizes the overall energy.
That's not clear.
It's
Because,
not connected. How does it
because the question was whether
Pre-melting films.
whether it's a
That's like egg.
So yeah.
whether it's a local or a global minimum is the problem.
Yeah. So
Can't necessarily get
yeah. So as long as everything's connected, of course, this is easy. As soon as, just like in any Pore-scale multi-phase simulation, as soon as you have multiple parts of the same phase, there's all sorts of questions that arise. What are the pressures of those? You know, do they actually have the same curvature? I mean, so you're opening a bag. I completely agree that you're opening a bag of worms, or a can.
In a slightly different way, do you have any idea of what the energy landscape is? I mean,
For this
going from 1% to 4%, are there minima that is hard to get to? Which is the energy.
No, so I don't have a visualization in my head of what this particular case looks like, but for the ones we did, essentially the energy landscape changed fairly. It wasn't bumpy. Let's phrase it this way. Okay. If nothing else, this
Was
would.
that for your one, the real shape, or was that for these idealized shapes?
Where the energy landscape is not bumpy.
Yes.
That was for the regular case. For the regular case, yeah. Because we did it for these little nucleations. Anyway, if nothing else, this would be the preferred. So when I showed this to several people, and there's actually petrologists have like, we've seen things where we have crystals where the melt seems to pool on certain crystal faces rather than others. There was a Nature paper early in the 80s on asymmetric zoning of crystals that was invoking things like this. But I agree. As soon as these things become disconnected, fundamentally you would have. I think it gives you an indication of what wants to happen. Whether it can, in terms of an evolutionary process, is a slightly different question. The reason that I was interested in this is like, well, can this induce anisotropies, and if so, how strongly, right? And so, again, this is very simple, but I think similar things will hold once we get really nicely textured material scanned. But so this is what this medium looks like if you look at multiple, at the actual network. And if you just use lattice Boltzmann to calculate the permeability in all directions, this F is just the aspect ratio. I have no idea we called it F. But it's essentially, so here you stretch it twice in the vertical direction. And what you see is this is the ratio of the vertical to horizontal permeabilities, and that you can essentially get 2 orders of magnitude larger permeability anisotropy than you have to stretch the grains. And it's
a ratio, so otherwise it's non-monotonic.
No. If you plot it in phi, there's a maximum, and the maximum occurs just before before it goes onto the faces. And then once it goes on the faces, it goes down, and it's probably because you have more friction. So it's complicated. But the other question is, so one is what is the actual permeability ratio? The other thing is, could this actually enhance the permeability in the direction of the fabric, which is a slightly different question. And again, this is the aspect ratio, and this is the permeability in lattice units. And you see that it increases maybe an order of magnitude. And so it's at least one mechanism. So, I think conceptually this may be interesting, and it would help make things flow faster in the direction of preferred alignment, and it would also maybe help to confine flow in that direction. And it seems that maybe some people have seen similar things in some of the ophiolites. Okay, and with this, let's see. Forgot why. With this to my favorite part here,
Why you assume that the stretching direction is vertical?
No, I don't.
Geological settings, it's most likely not to be. Things get squished horizontally.
Well, I'm trying to think of the pictures that the seismologists made of all their orientations. But either way, right? So the other thing, of course, would be interesting to do this if you have an alignment if there's anisotropy in the actual surface energies. So the other thing then now is hysteresis and the smelt network topology. So here we're thinking of a medium with constant dihedral angle of 90, and we're slowly melting it. So this is a succession of steady states. And so initially, of course, it's not connected. Here we're just plotting the curvature, and we should have probably just plotted the interfacial area, since that's a less And so we're increasing it. So what you want to imagine is essentially this material is melting, 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 melting. The pockets grow larger, they're not connected. And we're not showing we're just showing a cutout of the medium, right? It may look connected here, but it's not larger. And then eventually here, at somewhere around 14%, now it's clearly connected. You have big fat tubes. And you see there's a break in the evolution of the curvature as you melt it further. And now the question is, what happens if you now drain the melt and you do it slowly enough that you maintain textural equilibrium along the way? And you see that initially it's perfectly reversible and you're retracing your steps. And then as you hit the percolation threshold on the way up, the question is, does it drop down? And of course it does not do that. And this is, and so, because now it's already, it's in a different minimum, right? And so the question is, how far can you drain it down? And the answer is you can drain it down pretty far. And it remains connected to about 1%. And then it snaps off, and you leave some little pieces behind. Okay, and you can do the same thing with the permeability. You can calculate the permeability on these shapes. Of course, it's slightly less interesting because it's 0 initially, and then you go into some power law, and as you drain it back, that power law extends into the region that was initially within the percolation threshold, and only at the very end it kind of falls off the cliff. And so now you can add this, what we would call the trapping boundary, to this regime diagram. So here's for regular grains. So this is the percolation threshold. This is where you begin trapping. So inside here, it would be very hard to move any kind of melt as long as you don't shear it. Interesting enough, in the irregular grains, that trapping boundary is fairly independent of the dihedral angle and roughly about 1%, 1 or 2, 1.5%. So you can really drain the melt quite efficiently if you manage to connect it at some point. And here's just for comparison, forget the graph on the right here. This is some of the permeabilities that we're calculating in comparison to our results, are the colorful dots, and previous work is in black, various results, some experimental, some computational and theoretical. And so we see that we're within the scatter of all the previous results. One thing that you can see nicely is that the ones that have the highest permeability are the ones with dihedral angle of 60, because those are nice equant tubes. And then, of course, if you go to high dihedral angles, it does drop quite significantly. But also, if you go to smaller dihedral angles, the permeability becomes a little bit small. And I think this was mentioned in the talk about the transition zone. And that's just because you're beginning to spread the melt out onto the grains. And so your hydraulic radius goes down. So,
Mark, there are some other lab experiments for volcanic rocks that show the hysteresis effect too. I mean, not listed on your list, but I have it.
That'd be cool.
Yeah, remind me.
This is in bubble systems?
Yeah, it's a bubbling systems, yeah. Because you go from disconnected bubbles and they connect, and on the way back they have to pinch to go back to a bubble. So
truth be told, actually in the original Van Bargen and Waff paper, this is mentioned like in one line. It's just that their hysteresis loops look so small that people seem to have entirely forgotten about it. So now let me see. I have.
I saw the real system would have hysteresis.
Sorry?
And how you can calculate it. Why your calculation is history dependent at all.
Okay, so the reason it's history dependent, so we're solving, right, this is a succession of steady states, or if you want, you're essentially solving a elliptic problem that has multiple solutions, right? And so you're asking what determines which of those solutions our iterative algorithm converges to. And the answer is your initial guess determines. And so if you're, we're initializing with the last steady state, right? And that's what gives the sense of history. So when we're trying to calculate this guy, we use this on the way back down. We use this one as the initial guess, and that's where the sense of history comes in. And really, it's just a way to evolve towards that particular minimum in the energy landscape. But there's no way to prove it, but I do think that's what would happen in a dynamic system if you drained it slowly enough.
Mark?
Yes?
How about if you reverse the process halfway? Do you get the scanning curves?
So interesting. So we did in 2D. We played this game, and we got up to 4 different. So in 2D so yes, you can get multiple scanning curves. I'm not entirely sure why here. So we played with this a little bit, but we couldn't generate like beautiful scanning curves, right? So
If you at the place where it is a red circle, if you now start melting, what will happen?
we haven't done it. Well, so honestly, I think so we haven't done that, but honestly, I think it would just go back. So this system has some hysteresis, but I think it's much simpler than the two-phase system, which the two liquids in a porous medium, in a rigid porous medium system that you're used to look at. So there's some of these aspects, right? And clearly, you could introduce the interfacial area here as an additional descriptor, and then you could remove this hysteresis most likely. But I think it's somehow it's simpler, and I can't quite articulate why it is. Partly, I think there's less possible configurations because you're moving on a pre-existing grain boundary scaffolding, or whatever you want to call that. And I think that limits your possible configurations more than a gas and a liquid that can really do anything they possibly want in a pore space. But that's
But all this is restricted to dihedral angles greater than 60 degrees.
Oh yeah, no. And below it just goes forth and back on the same track, of course. So
Question about uniqueness.
Huh?
A question about uniqueness.
Well, I mean, clearly there is no uniqueness, right? So you have the same. So you have the same grains, you have the same porosity, you have the same dihedral angle. You have two solutions, and they're not both. When you compute the energies, one of them has a slightly lower energy. I forgot which one it is, but I don't think the overall minimum matters because it will be history dependent in a natural system. Okay, so here we go. Finally, some application. So I guess I got interested in this a long time ago, and so I've been following sort of this conversation about how, whether you can segregate high dihedral angle melts to form the core. And so obviously, here's a planet, here's the core, and planets are really complicated. There's Mars size impact, there's lake veneers, magma, ocean. It's a mess, right? So we're not gonna look at planets. We're just gonna look at planetesimals, right? So which is conceptually it's a potentially more profitable problem because it's smaller and less observations. Okay, so this is to scale. This is the Earth and this is Vesta. Okay, and this just to drive home how much smaller a system we're looking at. There are, of course, geochemical observations that suggest that a lot of these planetesimals formed cores very early on, and the question is how. But there's also the fact that the big planet may have actually been assembled from pre-differentiated little planetesimals. And so the non-surprising problem, of course, is that if you look at the dihedral angle that a iron-nickel type melt has on olivine grains, the angle is large, somewhere around 90 degrees. And so this has spawned a sequence of many papers that go on about what influences this angle. And always the conclusion is, well, if it's above 60, then we have a problem. We can't really segregate it. And if we can find some way to reduce it to below 60, well, then we have a nice simple mechanism for forming the core. And so one thing that you can play with is with pressure. If you increase the pressure enough, everything changes, right? And so the dihedral angle comes down. But in planetesimals, this doesn't really help you because you'll never reach those pressures. Other thing, of course, is you can shear it. But planetesimals are so small, they don't really have mantle convection. So there's no constant source of shear other than maybe the occasional impact. So I haven't done the calculation, but I've asked people that should know. But something to check. But and if there was any convection, it'd certainly be much less strong than it is on the Earth. So that's also not a likely mechanism. And then, of course, there's chemistry, right? And the problem with chemistry is that you have like many knobs. Here's just one of the earlier papers on this, and it shows that if you play with the composition of what's in a melt, you can affect this dihedral angle. My reading of the literature, which I don't understand entirely because it's complicated, is there's not yet really a satisfactory chemical way of bringing the dihedral angle all the way down. One possible way is very strongly oxidizing the system. But so if none of these, and I'm not sure how realistic is that this was a strongly oxidizing system. But so all of these potential solutions have their different problems, and so we thought we took a different approach. We just look at an actual meteorite that seems to capture this kind of process. So all of this work is done in the lab. And this has its own problems, and looking at meteorites has other problems. But here's a meteorite that seems to kind of represent what we're looking at, the so-called lodronite. So it's a primitive achondrite. What does that mean? Chondrite is something that has sort of the average composition of the solar system. An achondrite means that it's lost some of its original textural features and looks more like a mantle rock. And primitive, I believe, means that the iron hasn't been entirely extracted. But correct me if I'm wrong. Anyway, the name doesn't matter. So this is what it looks like. And so we thought, okay, well, let's, so here's some metallic alloy that, of course, is this core-forming melt, and the black stuff is the actual grains. And so what does this look like? And I apologize, we should have brought in these one after the other. Now there's too much to look at, but let's focus here. So this is the pore space of the iron-nickel alloy. And the first thing that you notice is that the porosity is 24%, which fundamentally is not surprising because like a third of the Earth is the core, and if this were uniformly distributed and the stuff melts like hundreds of degrees below anything else, well, then you'd have about a 30% porosity, right? And it's also clear that this is connected. So there really isn't, there certainly wouldn't be a problem segregating this melt. So now, unfortunately, what we realized is that the problem with looking at reality is that reality is complicated. There's also iron sulfide, now crystallized to troilite, and that, I've been told, was a immiscible liquid at the time that the iron was there. So you're not looking at a two-phase problem, you're looking at a three-phase flow problem, which sounds like there's a lifetime of entertainment right there. And if you add those two together, you get up to a porosity of about 30%. And so, unfortunately, what I'm going to show you here might throw into disregard some of the future slides, but it's interesting nonetheless. So, I only got this image like 2 days ago, but it shows you the relative distribution of the iron and the troilite of these two immiscible liquids. And the blue stuff is the iron, and the red stuff that is kind of transparent and looks ugly is the troilite. And what it looks like is like the troilite is really covering all the solid. Okay, so what it really looks like here is the iron-nickel alloy melt is the non-wetting phase, and the troilite seems to be the wetting phase that covers all the grain boundaries. So you're just going to ignore this for a moment. But so there's an interesting question if you have a natural sample and you want to ask, is this texture equilibrated, right? And so one way of doing this is to just, so this is the iron-nickel alloy surface, which we used to think was the actual pore space, but now we think it's maybe a liquid-liquid interface. And then you can plot the curvature on it. You can calculate the curvature and plot on it, and you see that it's largely green, which means it's largely the same curvature. And then there's some speckles, but those speckles could simply be from the fact that you're interpolating the CT image, which is a bunch of cubes. And so if you plot the mean curvature, it's actually surprisingly Gaussian, right? There's a preferred curvature. Now, I don't know if this, is this an acceptable spread in the curvature, but clearly there's a preferred curvature to the system, which is kind of nice. And you could use to argue that, there's it's trying to have a certain mean curvature. We also have an algorithm to compute dihedral angles automatically. So Sohail is an engineering student, and he literally would rather code for 3 weeks than spend one afternoon measuring by hand anything. We've tested this against some cases where people have hand counted the dihedral angle, and we get the same results. And because it's a natural system and because it's automatic, it's not as nice because obviously you measure everything and it's not quite as good. And there's clearly some sort of preferred angle here. We'll see. So if you would ignore the fact that this is two liquid phases, then you could conclude that this might be close to textural equilibrium, and there seems to be a dihedral angle around 80. Now, in recent light of the fact that there's two fluid phases in this pore space, one has to reevaluate this.
Yeah, it's an interesting question, is which one of them would set the dihedral angle as one?
So this is,
one mirroring the other?
The role of the advisor in this project has to be to call it a day at some point. But you do see, if you look carefully at the slides, you can see beautiful two-phase textures where you see, and now of course I don't remember which phase was on which side, but where you see a nice curved meniscus coming to a relatively what looks like a sharp angle at what is a solid grain. So it may be that that's what we're measuring here. Okay. Anyway, but so I guess fundamentally I just want to point out it's sort of an interesting question, how you would take a natural sample and then try to decide whether this was roughly approaching textural equilibrium or not. Yes?
You didn't point out, what's the relative grain size of the olivine grains relative to the metallic bits? Are they pretty much the same sort of size?
Okay, this is best answered by looking at a picture. There we go. Okay. I'm not sure if you can see this. So, the grain size obviously varies. So here are some grains, right? So I would say the pockets are certainly on the same order of magnitude. It's not, you have 30% porosity, right? This is what's really different here to, say, a mantle melt system. You have 30% porosity. So by definition, they're almost the same volume, but yeah, so grain sizes, here's a grain, right? Here's a grain. Does that help?
Yes. On your scanning, before you could separate the realize you had two liquid phases. Are you the pictures you showed? Are they of both phases, or could they originally separate the two phases, and they just map one of them?
So this is the interface. This is an outline of just the iron nickel alloy, and this is if you throw both the troilite and the iron together. And here we're trying to separate them. So the blue stuff. Does that answer your question?
Yes, it does, because you had separated the iron nickel alloy from the troilite right from the beginning.
So unfortunately, we did the analysis of the dihedral angle on the wrong surface. So, but here we go. I think really what I actually want to say is that, all the lab work, of course, is really interesting and really beautiful, but there may be a complementary line of investigation which just, looks at actual meteorites, right? But clearly this is, a high dihedral angle system. Everything is very nice and rounded, and it's connected, right? So let's just, okay. So I have this following idea that I think that in these systems, so if you have high porosity, I think that dihedral angle just doesn't matter at all, personally, okay? Because if you have 30% porosity, anything will connect, okay? Even if you had 180 degrees dihedral angle and you had a bunch of spheres at 30%, they would connect. And one of the reasons that we looked at the meteorite is because we weren't sure whether it was at all realistic that you would ever reach porosities that large. Well, the meteorite shows that, there are samples where the obvious thing happens is you melt all the stuff that melts early and you have 30% porosity. And if that's what happens, well, then you create a connected pore network, totally irrespective of the dihedral angle. And because there's hysteresis in the network topology, then you can drain it way past the percolation threshold. And this is, so it's actually very hard. In all these papers, people never, it's sort of an obvious, I think, thing, but this is never addressed in any of these. Only one paper actually explicitly addresses this, and they say, they noticed that, well, if you had a lot of melt, it would be connected, but they argued that if you drain it and you hit the percolation threshold, it would disconnect. But I don't think that's the case. And the other interesting thing is that our computations would suggest that you would leave a tiny amount of metal behind. And I'm not sure if that's realistic, or maybe this may be even, so there's this excess lithophyllum problem in the mantle floating around, whether this could at all speak to that, but it's an interesting fact. So then what we've done here, and this is, I'm not going to show equations, we've essentially put the two-phase flow equations together. We started off with 30% porosity. We put in our permeability that we've calculated for these networks. We start with we have a dihedral angle of 90 degrees, 100 kilometer radius planetesimal, and you just let it drain. And now, of course, in the center of the planet, the porosity approaches 1%, but the equations don't really make sense. But I don't think it's a problem, because what limits this is, of course, draining it out of the outer shell where the porosity goes very low. And yes?
Radiogenically heating this thing and solving
Not yet. We want to do the whole thing, so that's why this is not published yet. But so just a pure dynamic problem. So you assume you instantaneously melted 30%. Now, of course, it's going to be even faster if you gradually melt it, because it will start draining before it's fully molten, I think. We'll see. And what so for 100 kilometer radius planetesimal, you'll see that it would take, so this is the growth of the core as a function of time. For different dihedral angles, you see again that the dihedral angle itself doesn't make any difference. So yes, the higher dihedral angle drops the permeability by an order of magnitude, but I think what happens is just the porosity inflates itself up much more to accommodate the flux. And at least in this naive model, you're about done in 500,000 years. Yes, Rich?
Does the gravitational field evolve appreciably?
Yes. Yes, it does. So the one thing that we did take care of, that we had spherically symmetric gravity and revolving it as the core is segregating. The one thing, so I was not going to mention this, but since you've mentioned it, so what we find is that actually the core forms faster as we increase the planet. And that's because the driving force, G, so my student was like, he was like hesitant. He's like, why don't you send me those results? I wanted time of core formation as a radius of the planet. He's like, but it goes the wrong way. It like gets faster as the planet gets bigger. And I guess the simple answer is, you think that meteorite, right, that has uniform distribution of iron, has a radius of 10 centimeters. How long would it take to segregate all the metal to the center of that meteorite? And the answer is it would be infinite, right? I wonder if we haven't driven it out far enough. You would wonder if at some point. Anyway, all I'm trying to say is the other argument against high dihedral angle percolation is that somehow the permeability would be so low. And this goes back all the way to Stevenson, I believe, that the permeability would be so low that it just can't move fast enough. But clearly what this shows is you just, at least with the sort of Mackenzie equation, it just inflates the porosity to whatever porosity it needs to sustain the buoyancy flux, if you like. And with this, as promised, I think I can go on, but I think we should probably. So this is a natural place to kind of stop this. And so, just to wrap it up. So I think in these high porosity systems, the dihedral angle doesn't matter at all. And I think the only high porosity system that really matters is these kind of core formation scenarios. Obviously, if you're in a small degree of melting system. I'm very curious to hear if somebody has thoughts whether the fact that it suggests that we leave a little bit of iron behind, if it's a problem or if it may actually help address some of the chemical observations. Thank you.
Thank you very much, Mark. Do you have any further questions? Dan?
Do you know anything about the history of this meteorite?
This meteorite is fairly recent, so we are lucky.
What do you mean recent?
Recent.
Well,
Recent form or recent construction?
Well, so it's not a meteorite, but there's 50 papers on it. So it's owned by some guy in Arizona, and I found it by Googling on the internet, meteorite with 30% iron. And then I emailed the guy, and he sent it to me and said, what do you want to do with it? I was like, we're going to scan it, don't destroy it. And so we know, in comparison to some of the more well-known meteorites, we know very little of it. I think mostly for me it was a way to reassure myself that it's not somehow like I don't get it. Like it's possible. The obvious thing is possible that if you melt all the iron stuff, you'll have 30% porosity, and that porosity will be connected. I agree that obviously it'd be nice to know what the pressure and temperature and so on of that were. Unfortunately, he gave us 2 weeks. He said you have 2 weeks. Lunar Planetary Science Conference is coming up. You have 2 weeks to scan it, and you need to send it back because of other people that want to do work on it.
Such meteorites are not uncommon.
Yeah, well, so the interesting thing is that there's meteorites with a variety of amounts of iron in them. And we've been trying to get one to really make the point that you can actually drain into sort of the percolation threshold region. Would be nice to have a meteorite that had maybe 10% iron, and that iron is still connected. And we found a publication where somebody shows a CT image that shows exactly that. We've been trying to get it to sort of do our little textural equilibrium calculations on it. But the guy is now working for Schlumberger, and that's, it's not
the question is, I mean, what is you're assuming everything was in equilibrium. Right. Now, I mean, some of these ones, some of these ones, the iron gets distributed in completely different ways, quite out.
Well, no, I'm not saying that this is the answer, right? To all, there's obviously an infinite number of possible things that can happen to planetesimals. But all I'm saying is there's at least one meteorite that is sort of consistent with our naive view of what's going on. I think you have to give us credit to at least look at a natural sample as opposed to just experiments, right?
I'm not giving you credit. I just want to know more about it.
Anyway, so I think there's clearly a lot of interesting stuff that can be done. And so, we started this half a year ago, so but I wanted to show something real as opposed to just.
I was just going to say, I'm looking at primitive achondrites at the moment, kind of more from a core dynamo perspective, and so I'm very interested in this. But have you looked for any evidence of shock? Because the primitive achondrites we've looked at, we think they've been completely re-scrambled. So we might have got most of the metal into a core, there's been a big impact, and then that metal's been redistributed through the silicates. So I don't know that.
Yeah, so the only thing, I mean, you see that I mean, so I guess what I would say is that the way that the metal is distributed in this particular one is very close to what I would sort of imagine, coming from the textural equilibrium perspective. The only thing that is a little bit inconsistent with this, and I've conveniently ignored this, is there seem to be tiny, tiny thin films of something dense along all the grain boundaries, as if the whole thing had been just tiny, tiny little bit dilated. But they're very, very small, and they're conveniently too thin for the CT probe to pick them up. But if you look at a high resolution cross section, but they're extremely thin, and you can see very nice sort of dihedral angle type features. So I'm not really sure how that's related. I'm not sure what's the volumetric change as you melt the iron. Maybe there's just an actual volume change on the whole thing, and that's just a fact of trying to accommodate that. Again, I'm not arguing that this is happening in all possible planetesimals. I'm just saying there is a hopefully physically self-consistent way that you could segregate iron without either entirely melting it or totally destroying it with a shock. And which doesn't mean those things couldn't happen, right?
Yeah, so there's some papers that got out recently for the low melt fraction cases from Garapich and Fowl. Actually, they did these experiments with very low melt fraction. They have very high resolution images that you could use, and they have times because they did the experiment, they controlled it.
Is this where they're trying to answer whether you can have melt on the faces?
So you can have a look and test your model. I think will be nice because
they have to sequentially section, right? They have to sequentially. If you wanted to do this on a meteorite, you'd have to sequentially section it. I'm not sure the owner is happy.
They've done that to super high resolutions, and they also have the permeability. But you could look at the dihedral angles and the time it takes basically to reach textural equilibrium potentially. Yeah,
so it would be a very high resolution data set that we could
so it exists.
So that one of the interesting things, we did lab experiments ourselves, not on meteorites, but on salt brine systems, and if you, for those, to compute the curvature, it's all over the place. It does, the dihedral angle does seem to control the connectivity, but the interfaces are nowhere near as nicely uniform curvature.
Is that because salt's anisotropic with its interfacial energies? I mean, all of
so I guess there's olivine.
All the interfacial energies are isotropic.
In our forward simulations, yes, that's what we assume. Yes, and so that's the obvious reason, I guess. I'm not sure whether salt is cubic, I guess, right? So I think olivine would. Who knows what controls? But yeah, so that's an obvious reason why those experiments are not uniform curvature.
It looked like in those stretching calculations you did at the beginning that if you had included anisotropic surface energy, that it would have reinforced the preferential wetting that you already see.
I don't know. So one thing that I've learned is to stop making predictions. So what I actually sort of
slip system.
yeah, it probably depends exactly on how everything's oriented.
The low energy surfaces could be the same ones as the short edges, or they could not be. It depends on which slip system you have to take. If you have both crystal preferred orientation and shape preferred orientation, what fabrics we have.
Usually,
the fabric pictures that I've seen seem to suggest that you have both. So
you have both, and the face that is proposed to be the one that is preferentially wetted is the one that orients along the flattened planes also.
Which is sort of what we see.
Relation.
Right, we should probably move on to our next speaker.